remind my audience to subscribe to this HAPS channel to receive all updates on future broadcasts and on my YouTube channel as well. But now let's go straight to the real deal. Today we have a truly exceptional guest in the person of Dr. Jingmai O'Connor, curator of reptile fossils at the Field Museum of Chicago. Thank you so much for being here, Dr. O'Connor.
My pleasure. Thank you for inviting me to the Lair.
Yeah, I mean, I'm still not sure how that title will be received once this thing hopefully gets bigger, but yeah, for now I'm going to keep it. So you are again the curator of reptile fossils at the Chicago Field Museum, and more broadly, you are a paleontologist. And now, I would like to start from right from that, because when people think paleontology, I'm pretty sure you would confirm that their perspective is very much Jurassic Park biased. So what does paleontologists actually do, and what is paleontology actually like beyond what we see in movies or popular portrayals?
Yeah, okay. Well, we don't spend that much time trying to bring dinosaurs back to life, but there is at least one paleontologist who is trying to do that. And I'm like, didn't you see the movie? It doesn't end well, but yeah, power to him. That's Jack Horner, by the way. But yeah, paleontology is the study of ancient life. And we study it from fossilized traces. So, of course, the most fundamental part of paleontology is that you have to go out and find the fossils. So I think in that aspect, Jurassic Park was fairly accurate for that one scene. I'm going to admit that I am not a Jurassic Park fan, so I don't really remember how the movie goes, but I think there is one scene where they're out collecting fossils, right? So, being out in the desert, or not necessarily the desert, but a place we most often look in the desert, because in the desert, you don't have a lot of greenery, you don't have a lot of flora, so you have a lot of exposed rock, which makes it just easier to find fossils. But of course, you can find fossils almost anywhere that you have sedimentary rocks with the right kind of depositional environment. But anyway, so yeah, the most fundamental part is going out in the field, finding fossils. Of course, not every paleontologist does field work. There are some paleontologists who spend their entire lives in laboratories. There's some paleontologists who spend all their time in front of computers. Paleontology, especially in the 21st century, encompasses so many different things. And that's actually why paleontology these days is really exciting, because there's so many different techniques that are now starting to be applied to paleontology, which are revealing all sorts of new forms of data, which are then revealing new aspects about these extinct animals. Like, for example, there's this paleontologist who I really admire. She's just finishing her PhD right about now. Her name is Yasmina Weiman, and she's a chemist. So she's applying chemistry to paleontology and then discovering all these exciting things like, what color dinosaur eggs were, which is not just something that it's just a trivial thing. Now you can color them correctly in a reconstruction. This dinosaur egg color tells us about nesting behavior and aspects of the biology of these extinct animals. So it's really exciting. And, there are people who use coding to create algorithms to better understand how extinct animals are related to each other. And there's people who are doing experiments on embryos in order to understand the developmental mechanisms that have created the diversity of form that we see in extinct animals, or that have produced the diversity of form that we see alive today. So paleontology is really diverse science, and it can mean a lot of different things.
Oh yeah, I was especially interested in the point you mentioned that indeed paleontology, basically a paleontologist has to be versed in so many different aspects of science. You mentioned, for instance, chemistry, but also geology, because fossils are found mostly in rocks. So and ecology as well, perhaps. Once you find an extinct organism, you have to try to reconstruct what its environment would have been like. So it is basically reconstructing a world that doesn't exist anymore, and for that you have to look at every single aspect of what that world was like.
But not every paleontologist has to do the entire picture, right? So it's a bunch
Yeah,
of different paleontologists, each with their own very narrow speciality usually, and then each doing, working on one minuscule, like seemingly minuscule aspect of this, very complex extinct ecosystem with all its animals and plants and, even fungi or bacteria, everything that was alive at the time. You don't expect any one scientist to be able to be working on everything. So it takes like all different types of paleontologists to work together. Like I, for example, personally don't know anything about chemistry. I mean, I know a little bit, but I did really bad in chemistry in college. So I would have to collaborate with somebody like Yasmina to unlock these really interesting information through geochemical analyses, which is of course something I do plan to do.
It's actually interesting to hear to hear it from so many scientists that they were bad in chemistry in high school, myself included. Like make no mistake, like that's really something that sometimes makes me wonder. But well, anyway, speaking of going back for a second to the Jurassic Park thing, I mentioned that movie deliberately because it kind of relates, at least one of the most heated debates around it directly relates to your speciality, which is the long controversy about feathered dinosaurs, because purists maintain that velociraptors actually had feathers and were a lot smaller than those seen in the movie. So what is this whole fuss about feathers and dinosaurs all about?
Okay, well, so feathers are a feature that birds inherited from dinosaurs, but not just feathers. The arrangement of feathers on the forelimb forming a wing shape is also a feature that evolved in non-avian dinosaurs and was inherited by birds. And most of our, 99% of our information about which dinosaurs had feathers or proto feathers, which were much simpler structures than what we see in living birds. They were basically like stiff bristles, monofilaments, something like more like a hair but stiffer. So we refer to them either as proto feathers or dino fuzz. Of course, that was like a precursor to the complex feather morphology that we see in living birds. But anyways, almost all our information about the distribution of these integumentary, like skin structures in dinosaurs comes from early Cretaceous fossils in China. And these fossils, the first fossil in the Jehol biota, the first feathered dinosaur, was found in 1996. And it was this discovery that really cemented the idea that birds are indeed living dinosaurs. I mean, it wasn't a new idea. It had been around for a really, really long time. And there was ample evidence that this was the correct interpretation, that birds were dinosaurs. But still, people would, would take small issues and just refuse to accept that birds were dinosaurs. But then you discover feathered dinosaurs and you can no longer argue. I mean, you can, but it's just really strong, tangible evidence that birds are indeed living dinosaurs. Something that like anybody, just even a layperson, can look at that feathered dinosaur fossil and be like, yeah, I get it. I can see this connection between birds and dinosaurs. So these fossils revealed that basal relatives of T-Rex had feathers. And the first one that was found was called Dilong, and it's maybe 6 feet long. So it's a small basal tyrannosaur. So it preserving feathers was like, oh, okay, maybe only small T-Rex have feathers. But then another one was found, Eutyrannus, and Eutyrannus is 30 feet long. So that's 75% the body size of T-Rex. So now we have large tyrannosaurs that also preserve feathers. So then it's so now there's this really heated debate whether or not T-Rex had feathers. Whether or not Velociraptor or Deinonychus, which is also I know they call it Velociraptor, but the dinosaurs in Jurassic Park maybe actually look more like Deinonychus. But anyways, those are both dromaeosaurid dinosaurs. And whether or not they had feathers is not something you can really debate. We know that they had feathers. There's no reason to argue that they didn't. We don't have any direct evidence in Velociraptor or Deinonychus, but based on phylogeny and also body size, there's no reason to think they wouldn't have them. The only reason that it's an argument in T-Rex is because you could say that T-Rex is so big that evolutionarily speaking, it would be disadvantageous to have feathers in an animal that big. So that's why it's this argument, like, did it have feathers? Did it not? There is no direct evidence, though we do have T-Rex skin preserved. So we know that it wasn't fully feathered. I would argue that T-Rex had ornamental feathers, like limited patches of ornamental proto feathers that possibly were only present during breeding season, which may also be why we don't find them preserved, because it's only a narrow window of time each year when they would have had these structures. But but Velociraptor, Deinonychus, we have so many feathered dromaeosaurids from China that preserve wings on their forelimbs, proto-wings, because they're not used for flight, except in dromaeosaurids like Microraptor, which independently evolved flight, separate from the avian lineage, of course, and probably also Rhoneavis, another dromaeosaurid dinosaur that we, based on morphology, hypothesized could fly. Also probably would have done so with feathers, with wings formed by feathers. We don't have any soft tissue preserved, so we don't know. But we have like Zhenyuanlong, we have all these different dinosaurs preserving feathers all over their body, dromaeosaur dinosaurs preserving feathers all over the body, feathers on their arms, feathers on their legs, feathers on their tail. So it's pretty clear that Velociraptor and Deinonychus would have had feathers. I know that the reason that they didn't feather them in Jurassic World had to do with, it basically was too difficult to animate. This is something, because I was Googling this recently. I was like, because I know that Jack Horner told them, like, they have feathers, and why did they not listen to him? And I think it was just it's economics, it would have been so much more difficult to feather them. There's also a lot of people who really dislike feathered dinosaurs. There was this animated video that I remember watching like 5 years ago, and I had searched for it like a year ago and was unable to find it. But yeah, I don't know who we're allowed to cuss on this show, but it was basically like, F you dinosaurs, F you, because you used to be cool and now you have feathers and you're not cool anymore. No, it was like,
I've seen that too.
Yeah, it was like F science. That's what it was. Like, like F science, dinosaurs aren't cool anymore. But yeah, I can't find that video. So if you can find the link, please send it to me, because I have searched extensively.
Oh yeah, absolutely.
Unable to find it.
Like, yeah, one of the things that that I keep hearing about that is that feathered dinosaurs wouldn't look scary enough. But I'm like, I mean, people panic as soon as a seagull attacks them on the beach, and you're telling me that a feathered T-Rex wouldn't be scary?
True. Yeah, my PhD advisor, Luis Chiappe, would always this is one of my favorite Luis quotes, and he would say Jurassic Park is not the most famous dinosaur movie. It is Hitchcock's Birds. Also that's probably and they mention Archaeopteryx in that movie. So I'm like, yeah. But yeah, I mean, I think birds are terrifying. I think looking at living birds and seeing the way they the way their eyes move, the way their head and neck moves, and then extrapolating that information to something like a T-Rex is terrifying. If you imagine a T-Rex moving its head quickly, and we actually have information based on the skeleton, but also on the shape of the brain, which we can infer from using CT scans. If you look at the brain cavity, it's a good proxy for what the brain actually would have looked like. So then you can figure out which parts of the brain were big or small and understand its brain function, right? And these types of studies show that T-Rex would have had enhanced eye and head movement tracking, so it would have been able to follow a very quick moving prey. So it just hints at this type of behavior that we see in birds, the way that they move their heads. And I think that's just absolutely terrifying to imagine a T-Rex like that.
And there also goes, with what you just said, there also goes the T-Rex that can see moving things, that can see things standing still, myth that is all over Jurassic Park.
So T-Rex had vision that's better than an eagle. I think I forget what, it was 3.5 times better or something, but the point is it had really good vision. They say, or these studies on T-Rex eyes anyways, argue that the capabilities of the eyes of T-Rex were pushing the upper boundary of the capabilities of eyesight in a terrestrial vertebrate. So just practically the best kind of eye that any large terrestrial vertebrate could evolve. So excellent vision. It also had a really good sense of smell. So basically, you're not going to escape a T-Rex if, you know, one happens upon you. Your best bet, okay, like, you know, this is like paleontologists telling you, like, if you're facing a T-Rex, like, quote, the best way to save yourself, run. A full-grown T-Rex can only run about 11 miles per hour. So yeah, that's your best bet, is running.
Yeah, but also again something. Yeah, now I'm going on a tangent maybe. But like, if you actually were face to face with a full grown T-Rex, like would it even care about you? Because like as big as it was, like with the prey it was likely used to eat. Like, why would it waste time on such a tiny puny thing as a human being?
Well, because we would be pretty easy prey. One of the arguments for why T-Rex has enhanced vision is because it fed on prey that was difficult to catch. Like like other large theropods like Allosaurus probably fed on things like sauropods, and sauropods, they're defenseless except for their size, and they don't move very fast, right? But T-Rex, sauropods weren't abundant at the time that T-Rex lived at that's not a word, the latest Cretaceous, like 68 to 66 million years ago. So T-Rex most likely fed on things like Triceratops and hadrosaurs like Edmontosaurus. So Triceratops has these three really big pointy, horns, which were dangerous, surely. And Edmontosaurus is hypothesized to have complex social behaviors so that they, as a herd could have, worked together to try to evade predators. So because of this, T-Rex evolved like heightened senses in order to allow it to, to successfully hunt a more elusive prey or more difficult to, capture prey. So it was probably an ambush predator. I mean, like, it's hard to imagine something that big, like hiding in the bushes, like, oh, nobody's going to see me. But yeah, it probably was, ambushed its prey, and it had to it had to plan its strike very carefully to, catch, say, Edmontosaurus on its first strike before the herd starts doing its thing, or to attack a Triceratops before it and not get gouged by the horns, right? So anyways, these are just hypotheses, but there's just so much research that has been done on T-Rex because it's like just such a fascinating animal. I understand why people are so fascinated with it. It's, and there's so many still new things to learn, and we'll always be doing research on T-Rex and always figuring out new things. But yeah, I recently gave a talk on T-Rex, which is why I know all these facts. Before I started my job at the Field Museum, I will admit I knew very little about tyrannosauroids in general. I knew more about like the basal ones from China, and mostly what I knew was like they had feathers. Also, like some of them had crests, like Guanlong, which is pretty cool. But now that I'm at the Field Museum and we are the home of Sue the T-Rex, the biggest, most complete T-Rex that's ever been like published, anyways. I've had to, I have to obviously become an expert in T-Rex. But it's been really fascinating learning about it.
Oh yeah, well, it definitely is. It definitely is fascinating for me to hear about this, and I'm pretty sure I can talk in the name of everyone in the audience as well. But so now to if you don't mind, I will shift the focus away from T-Rex, at least for a moment, to go back to the link between dinosaurs and birds, because like you said, that birds are actually dinosaurs in their own right. So. If like you said, dinosaurs that were other than birds were evolved flight as well and feathers. So how do we know like when birds appear? Like what makes a bird if so many bird-like characteristics were also found in other dinosaurs?
Okay, that's a really good question. And the fact is that we don't have any characteristics that you can say, oh, this dinosaur has that character that makes it part of aves, which would be like the clade that is birds, right? And one of the reasons that it had always been difficult to understand what group of dinosaurs birds are most closely related to is because we didn't realize until quite recently that this high degree of homoplasy that was going on in this clade, Paraves, which is birds and its closest relatives, was due to the fact that flight had evolved repeatedly within this clade. So you have, we had all these features and we're like, oh, this feature is an avian feature, so perhaps it suggests a close relationship with birds with this particular dinosaur, for example, Microraptor. But now we actually realize that these features are not avian features per se. They're actually aerodynamic features that have been repeatedly evolved in the Dinosauria along with the repeated evolution of flight, and which happened right now, we estimate at least 4 times. Now, let's step back a little bit first and just say how we know that birds are dinosaurs, because I think it's a really interesting story. And it's a story that begins with the discovery of Archaeopteryx, which even today is still considered to be the oldest and most primitive Mesozoic bird that's ever been found, which is also what it was when it was first found, right? It was the first Mesozoic bird found, so that means it has to be the oldest, right? And also the most primitive known at that time. And that was in 1861, and now in 2021, it's still the oldest and most primitive bird. I know that you'll probably see people on, like papers that say Anchiornis is the oldest bird. I disagree with that, and I can tell you why later. But Archaeopteryx is discovered just 2 years after Darwin publishes his Origin of Species, right? And in the Origin of Species, he says, why don't we have any transitional forms? That's actually the biggest argument against my hypothesis, that I claim that there should be these transitions, but we don't have any evidence of it. And he said this is probably because the fossil record at his time was just really incomplete. And then Archaeopteryx was discovered, and he was like, yeah, look at this crazy bird. This shows that I was right. The fossil record is incomplete, and there's a lot of things we don't know about. He did not, I'm talking about Charles Darwin, he did not call Archaeopteryx a transitional fossil, but that's actually because they had found earlier, years before, they found giant tridactyl footprints, and they thought that were older than Archaeopteryx, and they thought that they represented birds. So they were like, oh, Archaeopteryx, at the time, they didn't think Archaeopteryx was the oldest bird. They thought those footprints were evidence of older birds. Now we know that they're actually belong to large theropod dinosaurs, not birds, right? But anyways, Thomas Huxley, who everyone knows as Darwin's Bulldog, because he defended Darwin and supported his, hypotheses regarding evolution through natural selection, but also because he has these big jowls and he looks like a bulldog. Anyways, so he studied Archaeopteryx, and he studied Compsognathus, which had been found from the same deposits. And he was like, birds are dinosaurs. Birds evolved from small carnivorous bipedal dinosaurs. But because no dinosaur at the time preserved a wishbone or furcula, which is of course present in all birds, this hypothesis was rejected by the general scientific community. And this idea was, reinvigorated numerous times. Nopska brought it up. He also thought birds were dinosaurs, but basically it lay dormant for 100 years until John Ostrom, an American paleontologist, is studying Deinonychus. And then he looks at Archaeopteryx and he's like, birds are dinosaurs. But again, people are like, no, we can't, we don't accept that. And there were lots of little stupid arguments for why they rejected this hypothesis. For example, Deinonychus being so much younger than Archaeopteryx, this is the so-called temporal paradox. We would expect the group of dinosaurs that's most closely related to birds to predate birds in the fossil record, right? So that was one major argument, which again no longer exists because of the discovery of the Yanliao biota in northeastern China, which is a biota that's 166 to 160 million years old. So just a smidge older than the Solenhofen limestones, which have produced Archaeopteryx, but they produce feathered dinosaurs like Anchiornis that are very, very closely related to birds and very similar to birds, but I would argue not birds because they don't appear to be flying. So I would argue that in the lineage of dinosaurs towards birds, you have to draw a line at some point and say bird and not a bird, right? So how would you do that? I would argue that it's the appearance of flight in the avian lineage. So I'm not saying that all flying dinosaurs are birds, but I'm saying in that lineage, that's where you should separate birds and non-avian troodontids, because I think that birds are probably troodontid dinosaurs. And Anchiornis has wings that are proportionately much smaller than those of Archaeopteryx, and the feathers are symmetrical. They're not asymmetrical. And asymmetrical feathers are really closely linked to flight. Like the only asymmetrical feathers in a bird's body are the flight feathers. And this asymmetrical feathers evolved multiple times. They evolved independently in Microraptor along with flight. And they also appear, in like Archaeopteryx, I would say, basically Anchiornis doesn't have this feature and its wings are proportionately smaller. So I would argue it's not flying. So I would say it's a non-avian troodontid. And I would argue that birds are avian troodontids. I mean, this is not something that is for certain. This is just a hypothesis. So right now we don't have any features that we can say this is a bird, it's not a bird, but we use a phylogenetic definition. So we just say that birds are the common ancestor of Archaeopteryx and Passer domesticus, which is like the common sparrow, and all its descendants. Those are birds. But we don't have any morphological features that are autapomorphic of aves.
So, like, now we're talking in a phylogenetic perspective, like you said, and I think that's a very interesting point to clarify, because when you said that you would put the point of so not divergence, but the point where birds first appeared on the evolution, on the appearance of flight in their lineage, then I can imagine someone in the audience wondering, but there are plenty of birds even today that don't fly, like ostriches or penguins or whatever. But yeah, so why does that not invalidate your hypothesis in phylogenetic terms?
So the loss of flight in some extant birds is a secondarily evolved feature. So they evolved from animals that were volant. So their loss doesn't mean that they get kicked out of the clade. It just means that they no longer have this feature. For example, whales are mammals, right? But whales no longer have hair, which is one of the features that defines mammals. But this is because they have secondarily lost this feature when they evolved into a marine environment. So did that make sense? I don't know if I can make it any more clear. For some reason, I find it difficult to discuss phylogenetic concepts, which is something I need to work on. This is like, I'm glad that we've re-identified this weakness in my science communication skill set. So I will work on this in the future.
Oh no! You definitely explained it very clearly. No, I just wanted to bring up that point, because sometimes when it comes to phylogeny, a lot of things look counterintuitive. I have to admit that not only when with dinosaurs and birds, but even like when I say to someone that the birds are the closest living relatives to crocodilians, and crocodilians have nothing to do with lizards, even though they look a lot more like them than to birds, then what I get is mostly confused and puzzled looks. So how, like, what traits, at least morphologically, because when it comes to DNA, it's a whole other matter, but for extinct animals, of course, we can do that. Like, for morphologically speaking, what traits do paleontologists normally look at to establish what clade an animal belongs to?
It's not any one specific trait. So what we do when we want to try to understand relationships is we'll run what's called a cladistic analysis. And I know that, yes, people who use DNA will use DNA information in their cladistic analysis. And of course, we don't have this available in paleontology yet. I'm just kidding. I don't think it's ever going to be possible. But like we have like dinosaurs preserved in amber now. So it's like, But yeah, no, these types of molecules degrade after like 1 million years. So we're never going to have Jurassic Park, just letting everybody know that. But okay, so what you do essentially is you take a new fossil, like say you have a new species and you want to know how it relates to all the previously known species. So in this cladistic analysis, you have a matrix, and the matrix has a set of characters. And what these characters do is essentially break down the entire skeletal morphology of an animal into numerical code. So the matrix will consist of, sometimes like 100, sometimes up to 900, even 1,000 morphological characters. And for example, one morphological character would be like premaxilla, which is like the bone here in humans. And it would say premaxilla, teeth present, would be a 1, and teeth absent would be, say, a 0, right? And so then you would code your specimen, like, oh, my specimen has teeth. So then I would put, like, I think I just said it would be a 0, right? I don't remember what I just said. Okay, but then you would do this for like every aspect of the skeleton. And then you would basically have reduced your skeleton into a bunch of numbers, and usually a bunch of question marks, because in a fossil, you don't usually have perfect preservation. So maybe one bone is missing, so all the femur characters are question marks, for example. Or maybe you only have one side of the bone exposed, so the characters for the other side of the bone, all question marks. You get what I'm saying? Anyways, you do this, and then you also have to code all the other taxa with which you want to compare the new specimen that you have with. Usually there's matrices existing that have already coded all these characters, so you just code your new character, your new taxa, and you add it in. And then you will run the cladistic analysis using analytical software, things like TNT, or the older versions were like Palp and Nona. And these software will use what I describe as like fancy mathematical algorithms in order to try to relate your taxa to the other ones. And you do this using a bunch of, you can use different parameters. I usually use parsimony, which is basically the idea that evolution is parsimonious, and that it is most likely that a given feature will evolve once rather than evolve independently a bunch of times. So for example, Archaeopteryx has a long bony tail, right? That looks like that of non-avian dinosaurs and also lizards. But birds have an abbreviated tail. So the tail is very short and ends in distally fused vertebrae, which is called the pygostyle. This has evolved multiple times. For example, humans also have an abbreviated tail that ends in distally fused vertebrae called a coccyx instead of a pygostyle. But anyways, so we would like hypothesize that all birds that have an abbreviated tail had a single common ancestor, and that the pygostyle in all birds that have a pygostyle was inherited from this single common ancestor. So it evolved one time. So that would be parsimony versus the pygostyle evolving independently in all birds that have pygostyles, like evolving like 4 or 5 times or something like that, right? So this is the parameters that you can set your analysis to use, and it will basically try to relate the morphology of your taxon to other taxa with the least amount of morphological steps, meaning like evolving from one feature to another. So from evolving a long tail to a short tail, it will try to like say, okay, that happened once, and that would be a shorter tree versus it evolving multiple times in all these different like birds, and that would each be an independent step, which would create a longer tree. Now, it is just a hypothesis, and we also know that, especially in the dinosaur-bird transition in this area of evolution, there's an extreme amount of homoplasy. So things are evolving repeatedly. So technically, it invalidates this hypothesis of parsimony, but so it is, it is a little bit confusing. And these cladistic analyses produce phylogenies that are only hypotheses. And these hypotheses are only as good as the data that's put into it. And let me tell you, like, it's not good data. Like, I honestly am very anti-cladistic analysis. I know that it's the best tool that we have, and I use it for sure, but I think people need to recognize the fallibility of these types of analyses, because you can manipulate them just like anything. It's not like, oh, this is the truth. This is an expression of what really was. It's not. It's an expression of the bias of scientists and like how they're looking at these animals, because the characters that exist are only the variation that we see. It's not true variation. It's our version of variation, if that makes sense. And also, depending on which taxa you include, you're going to get totally different relationships. And also, depending on how you score the characters, you're going to get different things. And people don't like necessarily agree on scorings, so people will score things differently. And yeah, anyways, I mean, it's a good tool, but I just think people put too much store in them, and they'll get an analysis, they'll get a result, and they'll start naming every node in it, and they'll start saying like, oh, this is how it was, and everybody's previous analyses were wrong, and like, it's, and whatever. I just think, that basically it's how we use cladistic analyses that makes cladistic analyses a problem. every form of human analysis has limitations and has flaws because it's human. It's made by us, and our flaws work their way into it. And I'm not trying to argue that we shouldn't use this tool. I just think that we should use this tool with caution and recognize its limitations. So, end rant. Sorry.
No, it was. I do think it was much needed. I mean, so yeah, that definitely. That was definitely a welcome intervention. And yeah, speaking of that, especially in paleontology, I would say that constructing an accurate cladistic analysis would be particularly difficult because, like you said many times, the fossil record is absolutely incomplete. And so why do we know so little about why is it so incomplete? Like, why do we know so little about what the world was like millions of years before we arrived?
Well, I mean, I guess it has to do with the limitations of fossilization, because only certain environments will even lend themselves to the formation of fossils. For example, if you live in a forest and you die on the floor of the forest, you're not going to become a fossil because there's no sedimentation going on in a forest, right? So you're not going to get buried. And even if there was some slow, gradual sedimentation, you're most likely going to get scavenged on before you could become fossilized. So that means of all life that is alive right now, not all of it is even possible for it to work its way into the fossil record. So that's one major limitation. Also, even for fossils that we do have, all we usually have is the skeleton, which is only a very small part of what makes up an organism. So you're missing all this. Even when you have a complete fossil, it's usually just a complete skeleton. So you don't know anything about its musculature, about its integument. I mean, these kind of soft tissues can fossilize, but they fossilize extremely, extremely rarely. So you can't rely on this as something that you can, as something that you have available to you to understand an organism. And then the other problem is maybe you have an exceptional Lagerstätten, meaning a deposit that has really good fossils, like, for example, the Yanlao biota or the Jehol biota that I mostly do work on. These are Lagerstätten, which is German for storage place. So it's just a deposit that has lots of fossils. And in these two deposits in China, you have exceptional preservation. So you have, like I was talking about feathers, right? Feathers are soft tissue. They commonly preserve in this one area. So you just have two patches of time, like 166, 160 million years ago, and then another patch 130 to 120 million years ago but are only recording a small area in northeastern China. And you have all this information from fossils from there, but you don't have similar information from fossils anywhere else that you can compare to. So you know what I mean? So you have to that also hinders our ability to interpret evolution in a broader sense. And then, okay, so you only have some environments that are forming rocks that are going to trap fossils in them, but then you're also limited by which of these rocks are going to be lifted to the surface of the earth and be available for paleontologists to dig in them. So, most of the rock is buried under other rock. It's like very deep in the earth. We can't get to it. It would be enormously energetically costly to get at these fossils. Like, for example, mining. It's also really bad for the environment, so we don't want to do that. So we're limited to what is exposed on the surface. And that means, and most of the surface of the earth, with the exception of like deserts and badlands, is covered with plants. So we can't even see we can't see the rocks, and we can't look for fossils in them. So it's actually there's this one area that I think is really cool in China. It's in, where is it? It's in Hezhou. So I think it's Gansu province, I'm pretty sure. So it's northwestern China. But if you went to this area and you were told this is one of the most fossiliferous areas in China, you'd be like, shut up. Like, there's no rock. Like, it's just green everywhere, right? But this area had been mined. So this area had been a source of dragon bones, traditional medicine, for thousands of years. And then, like, in the 80s, paleontologists was like, well, dragon bones are fossils. So all these like dragon bones that are being mined from this area, powdered up so that people can eat them, literally, like just tons and tons of fossils that got eaten every year in China until they like made this illegal fairly recently. And so then these paleontologists went there and started, collecting these fossils rather than letting them go into the traditional Chinese medicine market. So, but this area, so basically the way the farmers get these fossils is that they tunnel in the landscape. So there's no exposed rock, just like a green hill, and then this like dark little tunnel at the base of the hill that just goes in, and they're finding like full, rhinoceros, like fully articulated rhinoceros, mother rhinoceros with baby rhinoceros, things like Deinonychus, which was this like giant hyena-like mammalian predator. I mean, these deposits are Miocene. They're like 10 million years old. So you're not going to have any dinosaurs except for birds. But yeah, I mean, it's just incredible the amount of fossils that have been collected from there, but they're not collected by paleontologists. They've been collected by locals who were, had previously been mining these fossils for a totally different purpose. So, but like, so China, because it has such a high population, does get some, like through this, has gotten access to fossil deposits that normally wouldn't be accessible in a different, like, country, I guess you could say. Yeah, I don't know. Okay, I didn't really say that very clearly. But also the deposits in northeastern China that produce the Jehol biota. Again, it's a very green area, and all these fossils come from quarries. So that have like dug into the ground and just like systematically going through these deposits, which is also the same as the Solenhofen limestones in Germany that have produced Archaeopteryx and Compsognathus and all these other really exciting animals. So yeah, so the limitations are what gets fossilized, what parts of the animals get fossilized, and what paleontologists have access to actually being able to find millions of years later.
Right, and yeah, just one thing to the audience. So, if you have any questions for Dr. O'Connor, anything that you'd like to ask, please let us know in the comments, and Dr. O'Connor will answer it. So just shoot and take your time. And in the meantime, I have one last thing that I wanted to ask you, Dr. O'Connor, because, well, let's start from the beginning. Well, the first time I heard or actually read about you was in the book written by your colleague, Dr. Steve Brosate, where he basically talked extensively about your work on Mesozoic birds. And then I also read some of your recent interviews, and I thought it would be interesting to go over your personal story in academia and in science. So because it's basically it basically was a constant back and forth between the United States and China. And I can hardly think of two countries that are more at odds with each other right now. So what was your experience working both in the United States and in China? Also, since you have been vocal about this topic as a woman in a field that is mostly dominated by men historically, but also right now.
Okay, yeah, that's like a multi-pronged question. So you're probably going to have to like get me back on track once I like tangent off on episode.
Sorry. I always ask those kind of questions, and then it gets impossible to track back. So yeah, it's for me to apologize.
No. So I'll talk about like what it's like to be a woman in paleontology, and then I'll talk about what it was like being an American in China, I suppose, and also what it's like being a female scientist there. So, first I want to say that like I have heard a lot of bad stories, and I know that it can be very difficult for women in science. I was one of the lucky ones. Like I had wonderful advisors, never
And
sorry, I lost you.
Okay. Your connection fell for a second.
Sorry. But yeah, so I had wonderful advisors, wonderful, supportive, awesome advisors. And so I didn't have any difficulties myself being a female in science. In fact, I found that most of the times that I had like people being unfair to me and not very nice, it's usually other female scientists. And I do think that that's driven by the fact that they feel hyper competitive. Like, I'm in this male dominated dominated field, and everything's against me. So I have to do whatever it takes to succeed. And, who are the most vulnerable opponents, like, or competition that you can get rid of? It's young female scientists, female grad students, basically. And so I really think that that is, a tactic to just like to try to prevent other young female scientists from succeeding very early on. And it was very hurtful. I definitely remember like crying in my office a couple times, and like my advisor just being like, awkward. But yeah, but in the end, it didn't make me be like, okay, yes, I have to also do whatever it takes to make it in this field. And I'll like be cutthroat and whatever. To me, it was like, this is what I don't want to be. This is what I will do my best not to be. And I will do my best to support young students, females, minorities, whatever, also just young white males too. Like, anybody who needs support, I want to be there. I want to be, supportive. But one thing that has been like a fear that has followed me since when I was in grad school was, the department I was in was entirely white male. And there was like one Chinese guy, and then he retired while I was there. So it was like all white guys, geology department. And so they're hiring a new professor. And obviously there's a lot of pressure to hire somebody who's not a white male. And when you narrow it down to a small range of candidates, you have like 4 candidates, you invite them to come and visit, and they give a talk, and the whole department can see the talk, right? And so, I went to these talks, and there was one candidate who was by far the best, but unfortunately he was a white male. And then there was another candidate who was not very good, and also not a very nice person, but it was a female, and she got the job because the department was like, we can't have any more white males. And so that has been my fear my whole career, that I will get a job because I'm a female. And and I don't want that. You know what I mean? Like, I don't think that a new form of discrimination is not the solution to past discrimination. Like, oh, well, we have discriminated against women in the past, so now let's discriminate against white guys. Like, how is that going to help anything? Like, are people listening to themselves? You know what I mean? Like, and I'm not saying I have a solution, but but I just think that it's not the solution to just now discriminate against a different group, if that makes sense. So and it actually, when I got this job at the Field Museum, I was like, I hope I didn't get this job just because I'm a woman. And they're like, no, like, you did good. And I was like, but still, I have this fear. Okay, so then I moved to China, and China is actually a unique place because everyone's Chinese, right? So there's not like these issues with diversity and racism that you have in America. And also during when Mao Zedong was in charge of China, like, he basically empowered the female half of the population, because why would you cripple yourself by taking away power from half your population, right? If you want to move your country forward, empower everyone. So he said, women hold up half the sky, which I think is just such a cool quote. And because of that, women were treated as basically equals. And so you don't see the same discrimination against women in China that you have in the US. I'm not going to say that, people treat you exactly the same. Like, I remember going in the field, and I would try to like lift something heavy, and they would be like, oh, you're a woman, like, you don't have to lift that stuff. And honestly, I was like, fine, I don't care, like, sweet. But yeah, you could say that is a form of discrimination, and some people would maybe take offense to it. But I was like, I think I probably did take offense in the beginning, but then at the end, I was like, whatever, like, fine. But then, so then you might ask, well, what about, is there, discrimination against, me for being a foreigner in China? Look, for sure, there are some people in China who are anti-foreigners, and this has a lot to do with propaganda that has been perpetuated by the Chinese government for years and at different periods of time, right? So there are certainly some people who are anti-Chinese. I actually got beat up by a Chinese dude once, and I swear it was a hate crime. But anyways, That was like what a random tangent. But for the most part, people are in China are very curious, and it's something that I think is really beautiful. Like, you know, you get in a taxi and they stare at you like unashamed, just like staring at you. And I'll sometimes like stare back, like having this like staring contest, and I always lose. I'm always like, oh, like fine, you know, because it's like it's uncomfortable, like somebody sitting across from you on the subway just staring, you know, just staring. And like, but they're curious, you know, it's not hate, it's curiosity. And yeah, you could say it's rude, but like you have to remember that most of this population is not as well educated. Well, I was going to say America, but then I remembered that America is actually like really uneducated also. But I mean, a lot of these people didn't go to high school, you know what I mean? Like they, you know, so and a lot of these people came from rural areas and have just gone into Beijing for work, you know, and they've never seen a foreigner before, and they're really curious. And so taxi drivers, I would get this question all the time. They'd always look at me like, and then they go, "Where are you from?" And I would say, "I'm from America," or "Meiguo," beautiful country, it means in Chinese. And then I would always the follow-up question was, which country is better, China or America? And you know, they always ask this, which I think is funny. And I would always respond that you know, there is no country that's better. Like every country has strengths and has weaknesses. And you know, and then they were always kind of like, okay, you know, but there definitely is this like, you know, this, I guess this this idea that foreigners are all wealthy, you know, and I think this is because of the days when China was communist and Americans were the evil capitalists, and so we're all like, you know, wealthy, and relatively speaking, compared to the average Chinese person, Americans are, or you know, were more wealthy. But and of course, you know, I was like you know, had all my student loans and my student debt, so I was like, I'm not wealthy. But you know, for the most part, I found that China is a much, you know, it's a much more open environment than here in America, and I really loved my time there. You know, I actually never wanted to leave, but they wouldn't give me a green card, so I didn't have a
Oh,
choice.
okay. So that's how it went. And then yeah, sorry if this is maybe too personal. You said that in your experience, China is a much more open place than America does. Maybe another part of my question, which maybe got lost because I was talking too much, was that so was what was your experience of like being an Asian American scientist in the United States? And I was asking this just because, like, especially now, I see I'm hearing of a new wave of hate against Asian Americans in the United States.
Yeah, I mean, I think that I don't look Asian enough, that I haven't really. Well, it's funny. When I was a little kid, when I was in elementary school, you know, people would like pull their eyes, do the slanty eye thing, and like just like ching chong ching at me, you know, and yeah, it's not very nice. You know, I'm sure it did affect me. You know, yeah, I mean, I still remember it being as a kid, and it really hurt me then. But as an adult, I haven't experienced any racism that I can like recall off the top of my head anyways. I mostly get flack just for being myself, you know, because I'm loud and opinionated and not don't really fit in amongst most paleontologists. And I think there's, yeah, like, I don't know, maybe I would guess that it's jealousy, but I don't know. But a lot of people are, you know, they take they don't like me, you know, let's put it that way, and that's fine. You know, I'm an acquired taste, you know, like you like me or you hate me. But yeah, I mean, I've had a lot of people who are not very nice to me. People say very mean things behind my back, but like whatever, that's just you know, academia in general is a very highly competitive place. People are pretty nasty, you know, and this is something I always warn people about when they want to get into academia. I'm like, you need to know that it is like a pit of vipers. Like, yeah, there's a snake reference for you there. But yeah, like, you know, people like, and there's just so many things that are wrong with science because science is underfunded, and because we, you know, judge a scientist on how many papers they publish and where those papers are published and all these numerical things. And because science is so competitive and there's not enough funding, there's not enough jobs, I think it just breeds this this like antagonizing negativity, you know, and like when you get reviews, people are more often than not just nasty. Like, I mean, I would say I get like 25% constructive reviews and then like 75% just like nasty, mean. Their comments aren't even correct, not even valid, but the editor can't tell and just like rejects your paper, and you're like, yeah. I mean, it's so, you know, I've had, I guess, more people, you know, like being discriminated against me just because I don't fit in. That's what I would say. But then I went to China and I basically didn't have a presence in America. And I think this is actually something that's really messed up because, like, for example, my boss in China, Zhou Zhonghe, he's a member of the Chinese Academy of Sciences. He's a member of the American Academy of Sciences. He's one of the most important paleontologists in China and also of the 20th century, 21st century in the world. And he doesn't have a Wikipedia page because, like, you know, Western culture is just so Western centric, you know, they just like, you know, that's what they care about. And so even though China has so many amazing fossils, it's just like, it's kind of still seen as on the fringe. So in China, I had access to all these amazing fossils and I'm just banging away, like publishing, you know, on average, like 10 papers a year. Like, I think my max was like 18 papers a year or something. But I mean, I love doing research. So it's fun for me. It's something I enjoy. But then I made myself one of the leaders in my field. And now, like, you can't discriminate against me because I've already established myself. You know what I mean? If I tried to come up establish myself in Western society, I bet you I would have had a lot more difficulty. But now that I'm established, there's nothing you can do about it, right? Like, I'm here, you know, like, and yeah, and yeah, it's also funny because just based on my name, if you don't know me, people assume that I'm a male, which I think is odd because Jingmai sounds very effeminate to me. But I got Jingmai gated once on Twitter, which is one of the many reasons I screw Twitter. But anyways, yeah, like, but everybody was like, you know, like, like, you know, they were Jingmai gating me, you know, and then at one point they're like, it's a woman, and it was like, what does that have to do with anything? You know, like, does that make it worse or better? Like, I don't know. But yeah, it's. I don't know. It's, you know, life it's super complicated. And I think it's like all these, you know, people keep trying to be like, science has to fix society's problems. And like, we as scientists have to like fix the fact that there's low minority representation in science. It's like, look, these are greater societal issues that run really deep. And like, there's nothing that a search committee can do to fix those problems. I mean, yeah, I'm not saying that we shouldn't try, but I just think that, you know, we need to recognize that these are bigger problems and the solution is we have to go much deeper to get to the root of the problem rather than like superficially trying to treat it when you're already at the point of being a student in science. You know what I mean? Anyways, end rant.
Well, no, I always like to conclude interviews with a big in your face to academia, basically. So yeah, that's that's definitely. That was very welcome. I see there are no more questions from the audience, so I guess that's we have reached the end of our interview. So thank you so much again, Dr. O'Connor, for being here with us today. It was an extremely interesting talk, and I personally learned a lot as. Which, yeah, of course, I always say that at the end of every interview, but I mean it. I swear I mean it, and I'm pretty sure the audience will agree with me. So thank you again, and thank you everyone for tuning in today. The Snakeman's Lair will be back next week on the 14th with an interview to my personal friend, Dutch ecotoxicologist Rodi Blom, who will talk to us about the most dangerous animal on the planet, i.e., the mosquito. So yeah, I hope to see you there next week, and thank you again.
Awesome. Nice meeting you, Lorenzo, and thank you for having me.
Absolutely. Anytime.